And I want to talk about what this means and how this drives our design. Let's take a look. Here, I have the kind of table that you might actually work with when you work with analytical use cases. I have a table and it's got some name of some entity, some category, some facet this entity belongs to, and a bunch of additional data, X, Y, and Z. I have these very wide tables. And it is not unusual for you to interact with a table that's not just 7 columns, but 70 columns or more. In our work, we interact with tables that contain things like information about all the devices in a data center, and it's more than 100 columns. Many of those columns are not meaningful for some of the rows. And so it's 100 columns with a bunch of nones, with a bunch of missing data, because that's the formulation that the person who designed the table wanted to use. Well, these kind of formulations can lead to anomalies. And I want to share with you 3 types of anomalies, and then we'll think about why it is that they model those tables in that way. The first kind of anomaly is what you might call delete anomalies. Delete anomalies are anomalies where when you delete something from the table, you delete more information than you really wanted to delete. So for example, if I have these 3 rows, these 3 entities, the categories they belong to, and some minimum value corresponding to that category, and perhaps this also contains some value itself, you can think, if I add a value into this, you can think that, let's make sure this is valid as well. You can think that if I delete one of these rows, and let's put in the value as well. If I delete one of these rows, I've deleted a fact that I didn't really want to delete. The fact that I want to delete was what the minimum value is for category B. I deleted the fact that category B even exists. And so if somebody asked me, tell me how many entities we have for each of the categories, well, after delete, I'd say, well, we have 2 entities for category A. But the right answer might be 2 entities for category A and 0 entities for category B. But if I delete this, I accidentally, inadvertently delete more information than what I wanted. And with these very wide tables, it's very, very common that the only information that you have is stored in one of those columns. One indication that you are subject to these delete anomalies is when somebody says, what are all the unique possibilities for the category, for the facet, for the model, for the component name, for the manufacturer, whatever. And the only way to answer that is by doing a select distinct on a table that contains something that's maybe signal information or other data. If the only way for you to get what are the distinct items is a select distinct, there's no one table that is guaranteed to contain only the unique ones, then it's possible that, these are oftentimes modeling physical entities. If this is the data center, just because you don't have a row corresponding to an entity, a physical piece of hardware in a data center, doesn't mean that data center doesn't exist. It just means nobody's installed anything in that data center. Well, if the only way to know what the unique data centers that exist in the world are is to do a select distinct, then a delete of information about that data center can delete the existence of that data center, which is not correct. This is an anomaly. There are also insert anomalies. Insert anomalies occur when an insert would lead to conflicting information, conflicting facts. And so here I have the same information. I have each category and some minimum value that corresponds to the minimum bound for that category. And if I perform another insert for one of these categories, you can see a question arises. What's the minimum value for category A? Is it 100 or is it 500? If this were the data center and maybe its physical location, its street address, maybe they renamed the street. And if I perform an insert, I could have an insert with the new name of the street. But then what's the name again? Is it the old name or is it the new name? An insert has resulted in conflicting possibilities for what the actual real answer for a question like, what is the minimum value for this category? Or what is the street for this data center? The other very common type of anomaly that we see are update anomalies. And largely, update anomalies, you can kind of query your way around. And you can query your way around them pretty easily. An update anomaly occurs when you could partially update some information, but leave that information otherwise unupdated. And in this particular case, in the single table case, you can query your way around it. You could say if the category called A should actually be called AAA, we can perform an update. And we can perform an update, and we can make our update smart enough to make that change everywhere where it occurs. And so what's the big deal? If that category changes its name, we can correctly have that category's name changed everywhere. However, if there happen to be two separate tables that both record this information, then it becomes trickier. Because you can imagine that this update, well, first you have to remember to do the updates in both places, and second, you have to make sure that you do them within a transaction. You have to make sure that you do them all at once, because fundamentally when we're working with these database systems, they're asynchronous systems with multi-users. And so just because you can update something in two tables, update it here, doesn't mean that somebody can't run a query somewhere in between those two. There may be multiple users simultaneously running queries against this table, and that query is going to have some weird results if you've updated the category in one place but not in both places. We experience update anomalies all the time in our lives. Every time your landlord or your local government or the company that you work for sends mail to the wrong address, even though you went into their system and you updated your address when you moved. And they tell you, well, it doesn't flow into the other system. Oh, you actually have to update it in two places. It's an update anomaly. An update where the underlying fact changed does not reflect the changing of that fact throughout the system is an update anomaly, and they are extraordinarily common. In fact, they're much more common when you have bad modeling than insert anomalies or delete anomalies. And you can see that there is a certain presumption here. I keep saying fact, and I keep saying you have recorded something that is factually incorrect. There are two general perspectives when you think about databases. The first perspective is the database is a collection of correct facts about something. The second perspective is the database is a collection of data that is easy to process. When you think about how you design a database or a table, it is very common that if you are worried about the speed of processing, you'll choose these very, very wide tables where everything is next to each other, because it means the queries are very simple and the queries are relatively fast. You don't have to do joins to actually create the holistic view of what's happening in the table. You sacrifice your ability to store facts uniquely without running into delete anomalies, insert anomalies, or update anomalies. But you get fast queries. And you can think that if you're really using the database as just a dumb store of information that you can query out of core, and you can store lots and lots of data and it's relatively fast, that's generally what you're going to aim for. And this is why you often see these very wide tables. Because if you think about the database as, well, the data really matters, it has to be correct, it has to be factually correct, and I want to avoid incorrect facts, you couldn't use that approach. There's too much risk. Instead, you'd have to do some sort of normalization, which we will talk about in a moment. Except, in order to actually do something with the data, you're going to have to join it back up, which means more complex queries, potentially slower queries. That said, there's no reason why you cannot have both of them. There's no reason why you can't store the data in a factually correct fashion, and then via a view, a materialized view, or some sort of trigger mechanism, store it in an efficient to query approach. And so if we think about there being a data collection, a very permissive data collection portion of your database, a data analysis portion of your database, you might find that data analysis portion may itself have multiple steps. One step, which is the correct recording of underlying facts, and that might be somewhere between the collection and the analysis. It may be a data collection, a data modeling, and then a data analysis. And the data analysis might look like these very wide tables that everybody loves that are just really easy to do selects from, but oftentimes don't contain correct information. And if you think about it, here you can tease apart the analysis into the modeling of the data and the analysis. The analysis can still be very specific to the use case that you want to look at, but the modeling might be a little bit more generalized. Many different analyses need to understand this data in the same fashion where it's being pulled from the original collected data. And so that's insert, delete, and update anomalies, which is going to come up again when we talk about things like normalization and normal forms.